In large-scale machine learning, your training pipeline is only as fast as its slowest worker. We call these stragglers, and they are a silent bottleneck for distributed training. Traditional solutions like gradient coding promise to mask these delays by duplicating data across workers and using coding theory to reconstruct missing gradients. But here's the catch. That approach forces every worker to compute gradients on multiple data partitions simultaneously, multiplying computational overhead and often making training slower than just waiting for the stragglers. Today, we're breaking down a breakthrough solution called pipelined gradient coding. It keeps the straggler tolerance of coding theory while stripping away the computational bloat, matching the efficiency of standard distributed training and actually accelerating convergence. Let's start with the baseline. In distributed gradient descent, you split your dataset across workers, each computes a local gradient, and a master aggregates them. Simple, but if one worker lags, the whole step stalls. Gradient coding solves this by assigning each worker multiple data partitions. Specifically, you set C equal to S plus 1, where S is the number of stragglers you want to tolerate. Each worker computes gradients on all C partitions, combines them into a single coded gradient, and sends it up. The master can then decode the full aggregated gradient from any n-s workers. It's elegant, but computationally, it's brutal. Every worker now does C times the work per step. In practice, unless stragglers are severely delayed, that extra computation outweighs the time saved waiting. You end up with a system that's theoretically robust, but practically slower than the baseline it was meant to improve. Pipeline gradient coding flips this paradigm. Instead of computing all C partitions in a single step, PGC breaks the computation across time. Each worker rotates through its assigned partitions, computing just one per step. But it doesn't just throw away the work from previous steps. It stores the most recent gradients, and combines the fresh one with C-1 stale gradients from prior steps to form the coded gradient. The master still receives exactly one coded gradient per worker, decodes it exactly as in traditional gradient coding, and updates the model. The magic is in the pipeline. Per-step computation drops back to the distributed gradient descent baseline, while straggler tolerance remains intact. The trade-off is that the coded gradient is now an approximation, since it mixes fresh and stale gradients. But here's the critical insight. That approximation error is strictly bounded by the learning rate and the pipeline depth. In fact, mild staleness can act as a regularizer, smoothing the optimization landscape and speeding up convergence. PGC is implemented over two standard data placement schemes, fractional repetition and cyclic repetition. In fractional repetition, workers are grouped, and each group holds the same partitions. It's straightforward, and PGCFR works almost identically to standard gradient coding, just pipelined. Cyclic repetition is more flexible, but introduces a hidden trap. In standard GCCR, the master uses straggler-dependent decoding coefficients to reconstruct the gradient. When you pipeline this naively, those coefficients can explode in magnitude, sometimes reaching thousands. Why does that matter? Because each coefficient scales the staleness error of a partition. If a decoding coefficient is 7,500, your stale gradient error gets amplified by that factor, causing training loss to spike and diverge. The researchers solved this by relaxing the decoding objective. Instead of exact recovery, PGCCR targets an expected weighted sum where the average coefficient per partition is 1. By carefully designing the coding and decoding steps, they bounded the number of times any partition appears in the received gradients to less than 2, keeping error amplification strictly controlled. This subtle shift turns a divergent scheme into a robust, convergent one. Let's talk math, because this is where PGC really shines. Both variants are proven to converge geometrically under standard assumptions: strongly convex loss functions, Lipskitz's continuous gradients, and bounded stochastic variance. The convergence rate depends on a staleness parameter, which is inherently bounded by the pipeline depth and shrinks as the learning rate approaches 0. For PGCCR, the theory reveals something fascinating. Because gradients for the same partition come from different workers with different delays, the mixing of staleness actually averages out the adverse effects of stale gradients. It's analogous to variance reduction in asynchronous optimization. The contraction factor for PGCCR is strictly tighter than PGCFR, explaining why cyclic placement consistently outperforms fractional repetition in practice. The simulations and cloud experiments back this up. When training ResNet-18 on CIFAR10 and ImageNet across 12 workers, traditional gradient coding consistently takes over twice as long per step as the baseline, and that gap widens as you tolerate more stragglers. PGC, however, maintains a near-identical per-step time to standard distributed training, regardless of how many stragglers you're masking. But the real win is in convergence. Because PGC uses one partition per step like asynchronous methods, but recovers coded gradients that approximate the full aggregate, it reaches target loss thresholds significantly faster. In cloud tests, PGCCR reduced the total number of steps to convergence by nearly 55% compared to the baseline. It's the best of both worlds: the straggler resilience of coding theory, the computational efficiency of standard distributed descent, and a convergence speedup driven by controlled gradient mixing. Pipeline gradient coding isn't just a marginal optimization. It's a fundamental rethinking of how we handle stragglers in distributed training. By decoupling computation from the step boundary and leveraging the temporal dimension, It eliminates the computational paradox that has plagued coded distributed learning for years. If you're training at scale, the future isn't about waiting for stragglers or drowning them in redundant computation. It's about pipelining, coding, and converging faster. Thanks for watching. If you want to dive deeper into the full mathematical proofs and implementation details, check out the paper in the description, and let me know in the comments which straggler mitigation technique you found most effective in your own work.